I talked about Tor, and Tor, this is the lifetime of the species under investigation. We can imagine that if we generate the species at a given time 0, then it will take a time period Tor for it to fall to 1 over E, where E is 1.27 whatever, of its original concentration. It's got nothing to do with ignition delay times or anything like that. We're simply talking here about a single species and the lifetime of that single species in the reaction system that you're dealing with. And it's sometimes quite useful when you're looking at a mechanism and at a reactor to try to understand what the lifetime of a given species is going to be. And that's the way that you do it using those tools that I defined. Another thing is that I rather quickly skipped over going from a differential equation. So, for example, dOH by dt is equal to minus K OHH2. So this is the differential rate equation, to the integral rate equation, where I said that OH is equal to OH0 times e to the minus K times H2 times T. And of course, the way in which you do that is to take the OH to this side, integrate. So we take the OH to this side. Let's do that quickly. So we get dOH over OH. Take the T to this side. Sorry, the dt to this side. Let's put it properly. dt there. And then you integrate between OH0 and OH at time t. And you integrate this one between time 0 and time t. And then you get that integral rate equation. OK? So this is the differential equation, what we originally had. And this is the integral equation. And we also discussed C3H5. And so what we have there is that dC3H5 by dt is equal to minus 2 times K times C3H5 squared. Do exactly the same again. Take the C3H5 squared to this side, the dt to the other side, integrate, and you get the integral rate equation that I quoted. So I apologize for skipping over that and not going through it in detail. OK, any other questions that have cropped up over the break? Is that clear, what I've just said? OK. Everybody's happy, in principle. OK.
Well, when you say the secondary reactions are not important, are those just the reactions beyond the species you're trying to study?
Yep.
Okay.
So that was something that again was discussed over the break. So let me give you a more detailed example. So another point that was raised was, why is there so much emphasis on OH? And I'm afraid there's so much emphasis on OH because that's a species that I'm interested in. So there are other species that are involved in combustion, and we'll discuss some others in more detail later on. But as far as the pulse photolysis experiments are concerned, I'm afraid OH loomed very large. So for example, what we could do is we could use tertiary butyl hydroperoxide. Is everybody happy with that notation? So this is a tertiary butyl group with a hydroperoxide group, and we take a photon of light, and that produces those species there. And OH can react with H2. In this, if we have H2 present, OH reacts with H2 to form H plus H2O. And so we've got various species around, and OH can react with them. Okay? And what we want to do is to minimize them. And so the point is that we provided, in this initial experiment, we keep OH to something of the order of 10 to the 10 molecules per centimeter cubed. Then the concentration of these other species are going to be of that same sort of order. Okay? And so we want OH to react mainly with H2. And under our conditions, that's going to occur on a time scale of the order of 1 millisecond. But it's possible also for OH to react with this, or with this, or with OH itself, or with other species. And the time scales for those are going to be of the order of 1 over the rate coefficient multiplied by the concentration of that species, be it H or OH or 2-butoxy. The biggest value you can have here is, I mean, it could be larger than this, but it's of the order of 10 to the minus 10 molecules, centimeters cubed per molecule per second. All right? And so this time scale then is going to be of the order of 1 over 10 to the 10, which is the concentration here, multiplied by 10 to the minus 10, which is the rate coefficient, which is the order of 1 second. And that's much shorter than the experimental time scale of 1 millisecond. So, sorry, much longer than the experimental time scale. So these reactions are simply not competing with the reaction that you're primarily studying. So the secondary reactions you can forget about. So that's the advantage of being able to work with these relatively low concentrations. Okay, now I better get this right, because I see that Professor Hansen is standing at the back. So let's move on from what we were talking about there to another example, OH plus formaldehyde, again looked at by the Stanford group. So behind reflected shock waves, so they're working at higher temperatures than the instant shock wave, the OH radical was formed from shock-heated tertiary butyl hydroperoxide, which is the example that I gave over here for the pulse photolysis experiment. And the OH concentration time histories were determined from laser absorption now, using the R15 line on this particular transition in OH. And as I said, if this doesn't make any sense, then look at Professor Hansen, and you're not going to Professor Hansen's lectures, look at Professor Hansen's notes, and also look at the videos of his talks. Other reactions can contribute to the OH time profile, especially CH3 plus OH. And this is because it's a single-shot experiment, despite the sensitivity of the technique, it's necessary to work with higher concentrations. So secondary reactions are going to be significant, and you've got to take account of them. So the overall rate coefficient was determined by fitting to a detailed model, which was GRI mech, which we'll talk about on Wednesday, with the addition of acetone chemistry. The acetone comes from the tertiary butyl hydroperoxide. And they did a very detailed uncertainty analysis. It's a good paper to look at in order to understand the uncertainties that are generated in these sorts of experiments. So, so here's the OH profile, the OH decay, and there's the fit. The full line is the fit. The wavy line, slightly wavy line, is the experimental decay from the absorption profile. And then this is decreasing the rate coefficient for OH plus HCHO by a factor of 2. That's increasing it by a factor of 2, showing that there is very good sensitivity in the system to the reaction that they're looking at. And this is the sensitivity with respect to the OH plus formaldehyde here and the OH plus CH3 here. And you can see that the system is much, much more sensitive to the reaction OH plus formaldehyde, although there is this small sensitivity with respect to OH plus CH3. And then this shows an analysis of the uncertainties in the rate coefficient, the contributions to the uncertainties in the rate coefficient. So there is an uncertainty in defining the time zero. And then there's an uncertainty in the fitting itself. So fitting the reaction mechanism with this variable parameter, the rate coefficient you're interested in. There's an uncertainty that comes from that fitting. An uncertainty in the absorption coefficient. We need to know the concentration of OH absolutely. And the concentrations of the other species absolutely, what we're looking at OH. So getting that absorption coefficient, there's going to be a slight uncertainty in that, and that contributes to the uncertainty in the overall rate coefficient. The uncertainty in reading the wave meter, in which you set up the laser wavelength, because the absorption is going to change slightly as you change that, that wave meter reading. The uncertainty in the mixture, the reaction mixture that you set up. The uncertainty in the temperature of the shocked system. And then finally, the uncertainty in this rate coefficient, OH plus CH3 going to singlet methylene plus water. And so what they do then is to look at those overall uncertainties, and they combine them together to get a combined uncertainty in the rate coefficient ranging from plus 13.3% to minus 15.2%. So that demonstrates the detail that's been used in determining that overall rate coefficient. These are the final results, and this is a good slide that shows that there can be problems in combining together experiments from different laboratories. And so, so this is taken from the Stanford paper. So their measurements are here, and then a whole host of other measurements at different temperatures. These are, if you use these data down here, then the rate coefficient is well defined over a range of temperatures. But you can see that there are other measurements that have been made which give rise to really quite different values. And this is where data evaluation comes in, and we'll talk about that on Wednesday. OK, flow tubes. So as I said, those of you who've been on the lab tour will have seen Fred Dreyer's turbulent flow reactor. But flow tubes have been widely used for elementary reactions. And I'll mention one experiment very briefly. So this is the reaction between O plus OH. And interestingly, this is the reverse of the reaction H plus O2. And so this is an interesting reaction to look at from the point of view of detailed balance issues that we talked about earlier on. And so this is, again, an interesting and difficult reaction to look at because it involves two radicals. It involves O and OH. And so what they did was to flow nitrogen and argon through a microwave discharge, which generates nitrogen atoms. And then they injected water and NO. And the NO reacts with N to form oxygen atoms. And by a process of, by knowing the amount of NO that they've added here, and by changing its concentration, they can determine exactly how much O has been produced. So they know the concentration of O exactly. And then they used a flash lamp. They didn't use a laser. They used a flash lamp to photolyze the water and generate OH. And the oxygen atom concentration was very much larger than OH. So this was under pseudo first-order conditions, but the species that was involved, the majority species was O, was a radical. And they needed to know its concentration absolutely in order to interpret the experiments. And so they did that using this titration method because they're generating it from this reaction N plus NO. And then what they did was they used resonance fluorescence, which is a little like laser-induced fluorescence, except using a lamp rather than a laser, to excite the OH and then monitor its concentration as a function of time. And so the important aspect of this is that it's essentially a flow reactor because they need the flow conditions to generate the reactant species O using this discharge flow methodology. Another sort of flow reactor is this one from China. So this is using the synchrotron facility in China. And these are experiments described by Kai et al. In this paper here. And so this is the overall reaction system. So they have this reactor here with heating tape round the reactor. And they flow gases in. And then they have a pinhole and they extract. So these skimmers, they can extract species from the reaction system into the mass spectrometer. The mass spectrometer, once again, works using photoionization, using the synchrotron source for the photoionization, so they can distinguish between isomers very easily. And they can use it, because it's a mass spectrometer with a variable photoionization source, they can use it as a means of looking at many species in the reaction system. The reactor itself is fairly complicated because the pressure varies in the reaction cell. It's a narrow bore tubing, so there's a pressure drop as you go from one end of the reactor to the other. And the temperature also varies. It's fairly constant in the middle, but it's increasing and then decreasing rapidly towards the extraction point here. But they've characterized this reactor very, very carefully. And so they can interpret those experiments and extract rate coefficients from them and mechanisms from them. And so these are the concentrations of the various species. So these were experiments on butanol. So there's the butanol varying depending upon pressure and temperature. Here's butene, which is formed and then decays away. And here's the methyl radical. At low pressures, they can detect radicals in this system as well. The timescales are of the order of milliseconds or more, but they can detect these radicals, and they come in at higher temperatures, but they can only really see them at low pressures. And that's because at higher pressures, methyl plus methyl becomes too fast for them, for the reaction system. And so what they've done is they've taken the approaches that are used in the shock tube experiments to look at sensitivities so that they need, once again, a reaction mechanism. So a reaction mechanism, which in this case is really quite complicated, is an essential element, but they can probe this reaction mechanism. And so these are the sensitivities at 5 torr and at 760 torr for different reactions in their mechanism. And this is the sensitivity with respect to butene 1. So these are C4H sensitivities, Tmax 1450K, 5 torr, and 1100K, 760 torr in black. And so these are the mole fractions and fits to the mechanism, to the rate coefficients for particular reactions here, and varying those rate coefficients by a factor of 2. So this is an interesting technique which can look at lower temperatures, especially in the autoignition regime, and extract rate coefficients. Yeah?
So when you say the sensitivity is higher, does that mean you're getting, it's pushing the reaction, it's affecting the reaction more in the sense that you're getting more product, or?
No. So what this refers to is the sensitivity of the concentration of C4H8 to this particular reaction. So if you have positive sensitivities, then that's going to increase the concentration of C4H8.
Okay.
And negative ones are going to decrease the concentration of C4H8. And the bigger they are, the bigger that effect is going to be. So the sensitivity is basically that. So this technique is primarily of value in terms of testing mechanisms, but it can also be used to determine rate coefficients for particularly sensitive reactions. But you can see that many reactions are contributing to the sensitivity, so it's really primarily of value in terms of testing mechanisms. And so this is another example from the work that they've done looking at a fairly complicated mixture of systems. So this is cyclopentene oxidation and looking at different species, cyclopentene 1-ol, cyclopentanone, cyclopentene 2-ol. So these are all isomers, but they all, as we discussed before, have different photoionization thresholds, and they can, despite the fact that they all have the same mass, by using the photoionization thresholds and this photon energy curve, they can determine the concentrations of these different isomers in their reaction systems. Now, I won't dwell on this particular slide, but one of the important areas that we work on is autoignition chemistry, and so relatively low temperature oxidation of organic compounds. And there is a tendency to forget about the work which went before some years ago. And these are experiments which were done by Ray Baldwin and Roy Walker at the University of Hull using static techniques. So they used a reactor and they analyzed the products using gas chromatography. So very old-fashioned techniques. And I've just listed here, I won't go through them in detail, 3 methods that they used with references to them. So for example, what they did was to take a hydrogen-oxygen mixture, slowly reacting hydrogen-oxygen mixture, which is relatively well defined, and added an alkane to it and look at the products. And the analysis was fairly complicated. it relied on extensive application of the steady state approximation, but they got interesting chemistry out of it. And much of the early understanding of autoignition chemistry derived from these experiments here. A lot of the rate constants are wrong. They need reinterpreting, but the experiments themselves, they're wrong because either wrong assumptions were made in the analysis, the mathematical analysis of the results, or alternatively, wrong rate constants were used in that analysis. And so they can be reinterpreted, and it's a resource which I think we neglect. I'm somewhat biased. These are good friends of mine, so that's one of the reasons for bringing this to your attention. But there is a lot of information there that helps us understand a lot of autoignition chemistry with reinterpretation. Okay, what I'm going to do now, in the time that remains, is to have a look at experimental data and, in some cases, theoretical interpretation for reactions involved in the hydrogen-oxygen system that we mentioned right at the very beginning. But let's have a look at the ignition diagram for hydrogen-oxygen, which you all, I'm sure, know and love. And so what we've got here is pressure and temperature, and we get explosion or ignition on this side, and no explosion or no ignition on this side. And we get this interesting three-limit system. And we can understand a lot of it by just thinking about the interaction between branching reactions and termination reactions. So branching reactions generate radicals in the system. The initiation reaction generates radicals, but that's very slow. The main way to accelerate the reaction and to generate more and more radicals is through the branching steps. So branching produces radicals, and that allows us to move towards ignition. Termination reactions remove the radicals and take us away from ignition. And we can look at these limits in terms of the competition between termination, this first one, termination at the wall, and the branching step. Here's one of the branching steps, the more important branching step, H plus O2 going to OH plus O. There's also O plus H2 going to OH plus O, OH plus H. So the competition between these, as we go to lower and lower pressures, so as we come down here at a particular temperature, we go to lower and lower pressures, the radicals can diffuse more easily to the walls, and so termination begins to win over the branching step. So this is determined by the competition between H going to the wall and H plus O2 going to OH plus O. This second limit here is interesting because it depends upon the interaction between H plus O2 plus M forming HO2, which, as we said, is a very unreactive species. And we can think of this as a termination step, and H plus O2 going to radicals, the branching step. So it's the same reactants, H plus O2. One of them is leading to branching, one of them is leading to termination. And so this second limit here depends on that competition. As we increase the pressure, we increase M, and so we increase the relative fraction of these reactions that are going by this termination process. And so we move in from the ignition region to the no ignition region. And so finally, in the third limit, HO2 and HO2 are reacting, and So HO2 plus HO2 is formed from H plus O2 plus M, and this is winning under these higher pressure conditions. HO2 reacts with HO2 and forms hydrogen peroxide. As we go to higher pressures, then the dissociation of hydrogen peroxide, the rate of that reaction, but also the dissociation of hydrogen peroxide becomes faster because it needs energization of the H2O2 to occur. We'll talk about that in more detail tomorrow. So this third limit here occurs because we now get a new branching step where hydrogen peroxide dissociates to form OH. So HO2 is no longer a fully terminating species because it generates H2O2. The H2O2 dissociates and forms two hydroxyl radicals, and a branching step, and we move into this third limit region here. And these peninsulas, as we move to higher and higher temperatures, then we favor increasingly these branching steps, and we move over completely to ignition processes, so that this peninsula here gets smaller as we move to higher and higher temperatures. So that's a brief discussion of the interaction between these species, very much along the lines of those termination and branching step nature of the reactions that we talked about earlier on. How are we doing? Is everybody happy? No questions? Okay. Right. So we can have a look at a hydrogen-oxygen system. This is an old paper, but I put it up, well, it's not that old, it's 2005, but I put it up simply because it shows nicely the sensitivities. So these are the sensitivities defined in this way with respect to different reactions for different species. In this particular case, it's not a species, but it's the ignition delay time. So what we're doing here is replacing that by TOR ignition, where TOR now means the ignition delay time, not the TORs that I defined earlier on. Okay, so Jim Miller was looking at the sensitivities with respect to the ignition delay time for these different reactions here. It's a bigger reaction set than I showed you. I mean, a full reaction mechanism has something like 60-odd reactions in it. And these are at different temperatures, and it's at 1 bar and with this mixture composition here. And what I've said is note the significance of H plus O2 branching step, the termination step, and the H plus HO2 steps. Okay, so those are the ones with the big sensitivities. Okay, now just let's have a look at some of the data for these different reactions. We may not get through all of this, but we'll get through enough to help you understand what I'm trying to drive at. Okay, so here's H plus O2 going to OH plus O. And this is taken from a recent paper from the Stanford group, Hong et al. There's the reference. And so these are the various measurements that have been made. Well, this is a selected set of measurements that have been made for this reaction, covering a wide range of temperatures from about 1,000 K up to 3,000 K. These are measurements from Maston et al. These are measurements from Hong et al. And somewhat more scattered data from Paralia et al. And here's the fit from Hong et al. Now, one important paper that I would strongly encourage you to read is this paper with the first order is Mike Burke. International Journal of Chemical Kinetics last year. And this is an analysis led by Fred Dreyer and by Stephen Klippenstein, looking at all of the rate coefficients and making recommendations of the rate coefficients, the central rate coefficients for this hydrogen-oxygen system. And this analysis by Hong et al. Is supported by this paper by Mike Burke. So I strongly recommend you to look at this paper, but they discuss the Hong et al. Paper and its recommendation, and they support it. The reverse reaction we talked about earlier on. That was an example of a discharge flow experiment. O plus OH going to H plus O2. This has been studied under low temperature conditions, going up only to about 500 K. But the importance of this study is that it's difficult to look at H plus O2 under these conditions. So it's difficult to look at the reaction in the reverse direction under temperatures below 500 K. And so these give us the reverse rate coefficient, and then with the equilibrium constant, which is very well defined, we can get the forward rate coefficient. So this enables us to extend the range of validity or the range of experimental investigation of H plus O2 going to O plus OH using this reverse rate coefficient and the equilibrium constant. And so this is the overall rate coefficient for this reaction over this range 250 to 3000 K using these data, the other rate data for the reverse reaction and the equilibrium constant. So this emphasizes the way in which you can use forward and reverse rate coefficients to help define the rate coefficient through the equilibrium constant. Should say that this reaction here, as you see, decreases as the temperature goes up. There's no reaction barrier for the reaction. We'll discuss this more tomorrow. And so the rate coefficient decreases as the temperature goes up. The H plus O2 reaction, on the other hand, increases strongly as the rate coefficient, as the temperature goes up. Second branching step, O plus H2 going to OH plus H. So two shock tube measurements here, one by Sutherland et al. What they did was to use flash photolysis to generate and monitored O by resonance fluorescence at low temperatures. So they used flash photolysis at low temperatures and then shock tubes at higher temperatures. And they generated O in the shock tube using flash photolysis. And then they monitored using what's called atomic resonance absorption spectroscopy, which is using a resonance lamp corresponding to the oxygen atom and measuring the concentration by looking at that an absorption of that light. And so there's the reference to this paper, and then a paper by Davidson and Hansen and the Stanford shock tube, generating O again by laser flash photolysis of NO and pyrolysis of N2O, and O monitored by atomic resonance absorption spectroscopy. So these are interesting shock tube measurements using pulse photolysis also to generate reactive species. Right, H plus O2 plus M. So this, remember, is the termination step. It's the alternative reaction of H plus O2. In this case, generating HO2, which is this unreactive species. The reaction is in what's called the third order limit, except at higher pressures. Let me remind you what I said earlier on. if we look at this rate coefficient as a function of pressure or of the concentration of the third body, then it looks something like that, where this is K infinity, and this approaches a limiting slope where K is equal to K0 times the concentration of M. And the reaction is HO2, sorry, the reaction, what are we looking at, is H plus O2 plus M. And so in this region here, the reaction is actually third order. So the rate is equal to K0 times M times H times O2. So it's a third order reaction. And so we refer to this region here as being the third order regime. And for reasons which I hope will become clearer tomorrow, this particular reaction is very much in the third order limit under normal pressures. If you go to very much higher pressures, then you can move it up into this region here. So experiments, Michael et al. Did a wide range of experiments using flash phosphorescence at room temperature and a shock tube at higher temperatures, argon, oxygen, and nitrogen as third bodies, and also water. And they found that water had an unusually strong effect. Water is a very, very efficient third body. Remember, the function of the third body is to remove energy from the adduct HO2. And water is particularly effective at doing that. And that's important in combustion systems because there's quite a lot of water around. And the paper shows a detailed analysis of energy transfer parameters. So these are results taken from that paper, and this is showing the unusual effect, unusually efficient effect of water. The Troy group in Göttingen used a high-pressure reactor. So this is they're looking at HO2 in absorption, spectroscopy at 230 nanometers. So they're looking at the formation of the product. And they're doing this they're generating H from photolysis of ammonia at 193 nanometers. And they went from 1.5 bar up to 950 bar. So these are really quite high-pressure experiments. And at these higher pressures, the reaction moves further into the fall-off region. And so here's a profile of HO2 formation here. So they get the rate coefficient from the appearance of the HO2 there. And then these are the rate coefficients as a function of argon concentration and at different temperatures. So temperatures going from 300 up to 1200 K. And the argon concentration is going up to 10 to the 23 molecules per centimeter cubed. So of the order of, well, they don't quite get up to there, but they go up to about 1,000 bar. And they took the data for different third bodies, and they showed that using a certain analysis, they could condense all of the data onto a single curve, which is a good way of presenting the data and of analyzing the data. So different third bodies have different efficiencies, but by scaling them using, so what that means is that if we use different third bodies, the curves look something like that. They all go to the same limit, the same K infinity, but they have different slopes at zero pressure. And if you look at that paper, you can find just an explanation of this scale down here, which is essentially a pressure scale, but a way of scaling according to the value of K0 and the value of the high pressure limit. And so with these, they can then get a good analysis of this reaction system under a wide range of conditions that's of value in combustion, especially combustion occurring at relatively high pressures. And this is an evaluation by Burke et al., this paper that I told you about. And so you can see the paper for a detailed discussion of the way in which they've analyzed the data using this methodology that I mentioned there. Now, just let me say a little bit about these pressure dependencies. So what we said was, if we take A plus B, it forms this energized AB star, which can then be stabilized to form AB. And the rate coefficient can be expressed in this form, Ka Ksm over K minus A plus Ksm, using the steady state approximation. And we can define limiting values K infinity and K0. And if we substitute those in there, we get this form for the rate coefficient. K is equal to K0 times M times K infinity over K infinity plus K0 M. And you can have a similar treatment for dissociation reactions, an exactly equivalent treatment for dissociation. And this is what's called the Lindemann-Hinshelwood model of pressure-dependent unimolecular or termolecular reactions. The treatment is an approximation, though, because, as we'll see tomorrow, K minus A depends upon energy of AB star. The more energy AB star is, the bigger K minus A is going to be. And this simple analysis assumes that it's constant. In addition, deactivation by this third body doesn't take place in a single step. It takes place in several steps. And that, again, leads to the invalidity of this expression here. And these have the effect of broadening the fall-off curve. So if we look at the fall-off curve, it gets broader. So it approaches this high pressure limit more slowly because of these two effects. And Jürgen Tröer in Göttingen developed a parameterization methodology which takes account of that. And any of you who use chemical mechanisms will have come across these ideas in Chemkin. So Chemkin incorporates the Tröer methodology. And what it does is it takes that simple expression that we had and multiplies it by a parameter f, which depends upon pressure. And so it depends upon pressure here and a string of constants, and this parameter f cent. F cent is the value of f in the center of the fall-off curve. And so if we want to parameterize this rate coefficient, then we fit K0 and K infinity to modified Arrhenius expressions. For example, K0 is A naught, T to the N naught, E to the minus E naught over T. And a similar expression for K infinity, the high pressure limiting rate coefficient. And F cent is fitted to something of this sort with three parameters, T triple star, T star, T double star in this overall expression here. And so if you look at a chemical mechanism that's been set up within ChemKin using pressure-dependent rate coefficients, then you'll find parameters of this sort, and they relate to these modified Lindemann-Hinshelwood expressions for these pressure-dependent reactions. Okay, and if we go back, then you'll find a discussion of these for this particular reaction, H plus O2 plus M, in this paper by Michael Burke et al. Okay, we're running out of time, so what you can do is just look through the notes for the final slides, and if you have any questions, then please do come and talk to me. But there's nothing fundamentally different in the next few slides here. There aren't very many of them. But if you have any questions, then do please come and ask. If you have any questions that you think we ought to discuss generally, then raise them with me now or raise them with me tomorrow morning. But for now, that's enough on these experimental determinations. And what we'll do is we'll talk about theory tomorrow morning at the same time, 8:45. Thanks very much.